Imagine you're in a car,
Right.
just cruising down the highway at like 30 miles an hour.
Okay, setting the scene.
Yeah, and then suddenly the car hits a brick wall, the metal frame just crunches, decelerating to zero basically instantly. But what about your body?
Right, that's where the physics gets very real.
Exactly. Without a seatbelt, your body is still doing 30 miles an hour. It doesn't know the car stopped. It's just going to keep moving forward through the air at that exact speed until it finds something else to stop it, which is, usually the steering wheel.
It's a terrifying thought, honestly.
Totally terrifying.
Yeah.
But today, we're diving into the invisible laws that govern that exact moment and, well, virtually every other movement in the universe.
Yeah, because to really understand why that body keeps moving, we have to look past our basic assumptions. We experience the physical world every second, so we think we intuitively get the rules.
Right, like I drop a glass, it breaks. I push a door, it opens.
Exactly. But the underlying mechanics operating behind the scenes are this completely invisible architecture.
Okay, let's unpack this. We have a massive stack of educational notes, historical records, and exam prep material today on force, motion, and Newton's laws.
It's a lot of ground to cover.
It is.
Yeah.
So whether you are, up late cramming for your TEAS or HESI nursing entrance exams, or you're just insanely curious about why the physical world behaves the way it does, this deep dive is going to arm you with the answers.
And we're going to make it accessible.
Yes, for sure. We're looking at the core rules, the history that shaped them, and how this directly applies to saving backs and saving lives on the hospital floor. So let's start with the basics. What are we actually talking about when we use the words force and emotion?
Right. So a force is basically a push or a pull exerted on an object, and that happens due to its interaction with another object.
But it's not just like a vague measure of strength, right?
No, not at all. In physics, forces are vectors. That means they require two vital components. You need magnitude, which is the amount of the push, and direction.
Okay, so pushing forward is totally different from pulling down.
Exactly. A force of 10 pushing forward is entirely different from a force of 10 pulling down. And we measure this magnitude in newtons, named, of course, after Isaac Newton.
Which sounds incredibly abstract to anyone trying to study for a test.
Yeah.
I mean, I know what a pound is. I know an ounce. What does 1 Newton actually feel like in the real world?
Think of it this way. Holding a single average-sized apple in the palm of your hand requires about 1 Newton of upward force.
Oh, wow. Just to fight gravity.
Just to fight gravity and keep it from falling, that is your physical baseline. As for motion, that is simply a change in an object's position over time, but it has to be relative to a reference frame.
I mean, you need a background to compare it to.
Precisely.
Like if you're sitting on a smoothly moving bullet train with the blinds pulled down, you don't feel like you're moving at all. Relative to your seat, you're stationary.
Right, but if you open the blinds and look at the platform outside, you see you're absolutely flying by. You need that external point of reference.
Which brings us to the core mystery. Because for centuries, philosophers could observe motion, but they deeply misunderstood its nature.
They really did.
Yeah, because before we can calculate how things move, or how many newtons it takes to move them, we really have to look at a centuries-old misconception of why things stop. I have to play devil's advocate for a second here.
Go for it.
So the notes say the Greek philosopher Aristotle believed an object needs a continuous pushing force to keep moving. Remove the force, and the object seeks its natural state of rest.
That was the accepted truth for a long time.
And I get why. I'm looking at my coffee mug on the desk. If I push it, it moves. If I take my hand away, it stops immediately. Aristotle makes complete sense to my everyday intuition. So why was he wrong for 2,000 years?
Because, frankly, human intuition is a terrible physics teacher. It appears as though the motive force is gone and the mug simply gets tired. But what Aristotle missed is that rest isn't a natural desire of the object.
Wait, really?
Yeah, the mug stops because of a completely separate, invisible force actively working against it, which is friction.
Oh, right, friction.
The microscopic bumps and ridges on the bottom of your ceramic mug are literally crashing into the microscopic bumps on your wooden desk, grinding away its kinetic energy.
So the mug isn't choosing to stop. It is being forced to stop.
Exactly. But to realize this, you had to imagine a world without friction, which is incredibly difficult for the human brain to do.
Because friction is just everywhere.
Right. Galileo started to piece it together by rolling balls down extremely smooth inclined planes, noting that they rolled further as friction decreased. René Descartes theorized about it philosophically, but the true breakthrough happened in total isolation.
Ah, right, the plague.
Yes. During the years 1665 to 1666, Cambridge University closed due to the Great Plague. So a young Isaac Newton retreated to his family home, Woolsthorpe Manor.
Just a guy in his 20s, working from home during a pandemic, fundamentally rewriting the laws of the universe. I mean, no pressure.
Seriously. It was his Annus Mirabilis, his miracle year. He synthesized Galileo's observations and Descartes' ideas, and he combined them with his own brilliant insights into gravity.
And that gave us the first law.
It did. He formulated what we now know as the first law of motion, the law of inertia. Though he didn't formally publish this until it was 44 years old, in his massive 1687 work, The Principia.
A project that almost didn't happen, right? The notes say the Royal Society basically ran out of money.
They were broke. It was actually Edmund Halley, the astronomer Halley's Comet is named after, who stepped in and paid for the printing out of his own pocket.
I love that a book that changed human history was essentially self-published with help from a friend. So let's look at what that book actually said.
Let's do it.
The first law states, an object at rest stays at rest, and an object in motion stays in motion at a constant velocity, unless acted on by a net external force.
And that underlying stubbornness of the object, that's called inertia. Inertia is an object's inherent resistance to any change in its state of motion.
So bigger objects have more of this stubbornness.
Yes, the more mass an object has, the more inertia it has.
Let's bring this into the physical world. The classic magician's tablecloth trick is, entirely about inertia, right?
Completely.
You have a fully set table with heavy plates, glasses, and silverware. The magician yanks the tablecloth out, and everything stays exactly where it is. It looks like magic, but it is just a mechanical exploitation of the first law.
Exactly. The plates have a high mass, therefore a high inertia. They demand to remain at rest. The trick relies entirely on minimizing the opposing force, which, again, is friction.
By jerking the cloth super fast.
Right. By jerking the cloth incredibly fast, the magician minimizes the duration of contact. The frictional force acts for such a brief millisecond that it cannot overcome the heavy inertia of the dishes. They stay put.
That perfectly explains the car crash scenario we opened with.
Okay.
Car hits a wall and experiences a massive external force, bringing it to a halt.
But your body has its own inertia.
Yeah, it demands to keep moving at 30 miles an hour.
Yeah.
The seatbelt provides the necessary external force to stop your passenger inertia. But the notes highlight an even more specific medical application of this, which is whiplash.
Whiplash is a perfect, though unfortunate, example of inertia. In a rear-end collision, a stationary car is struck from behind and accelerates forward rapidly.
Okay, so the seat pushes your torso forward.
Yes. However, your head, obeying the first law of inertia, wants to stay exactly where it was. Because your torso moves forward and your head tries to stay still, the head lags behind, violently snapping the neck backwards.
Ouch. So headrests aren't just for taking a nap.
Not at all. Headrests are not designed for comfort. They are anti-inertia safety devices. They provide the external force needed to push your head forward simultaneously with your torso.
Wow. Okay, so if inertia is an object's stubbornness, how hard do we actually have to push to break that stubbornness? That is where the math comes in, right?
That's where we get to Newton's second law. The most famous equation in mechanics, F equals ma.
Force equals mass times acceleration.
Right. This law translates the concept of pushing into precise mathematics. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass.
Okay, let's visualize that inverse proportionality. Imagine you are in a grocery store parking lot. You have an empty shopping cart, which has a mass of about, say, 15 kilograms.
Okay, standard cart.
You apply a 50-Newton push, it zooms forward, the acceleration is high. Now apply that exact same 50-Newton push to a stalled pickup truck with a mass of 1,500 kilograms. It barely creeps forward an inch.
Same force, but because the mass is astronomically higher, the resulting acceleration is astronomically lower.
It just makes so much sense when you picture it.
Well, let's scale that up from a grocery store cart to the Apollo missions. Think about NASA's Saturn V rocket on the launch pad.
Well, this is a massive leap.
It is. To overcome the inertia of a fully fueled vehicle with a mass of 2.8 million kilograms, the engines had to produce 33.4 million newtons of thrust.
It is hard to even fathom those numbers. 33 million newtons.
What's fascinating here is how the second law dictates the visceral, physical experience of the astronauts inside the capsule during launch. As the rocket ascends, its engines are constantly burning fuel.
Which means it's expelling thousands of kilograms of mass every single second.
Exactly. The rocket becomes lighter.
But the thrust from the engines, the force, that stays exactly the same.
Correct. According to F equals ma, if the force remains constant but the mass steadily decreases, the acceleration must increase.
Oh, wow. I never thought about it like that.
Yeah, the astronauts don't just feel a constant heavy weight on their chests. They feel increasing g-forces pressing them deeper and deeper into their seats as the launch progresses, because the shrinking mass allows the vehicle to continually accelerate at a faster rate.
That is wild to think about. But it raises a huge question. We know force causes acceleration, but where does the force actually come from? You can't just have a push without something doing the pushing.
And that leads us perfectly into the third law, the law of action and reaction. A force is not something an object possesses, it is an interaction between two things.
So it's always a pair.
Always. For every action force, there is an equal and opposite reaction force.
We experience this without even thinking about it. Like when you walk across a room, your foot pushes backward against the floor. That is the action.
And the floor pushes forward against your foot with an equal amount of force.
Which is literally what propels your body forward. And that explains why walking on a sheet of smooth ice is nearly impossible, right? The friction is so low that your foot can't push backward effectively, meaning the ice can't push you forward.
The exact same interaction governs rocket propulsion in the vacuum of space. People often assume a rocket needs air to push against in order to move.
Right, like a bird flapping its wings against the air.
Exactly, but the third law requires no medium. A rocket engine pushes exhaust gas out the back at high velocity. That's the action. The exhaust gas pushes the rocket forward with an equal and opposite force. That's the reaction.
The mass of the rocket and the mass of the gas just interact with each other.
Exactly.
Okay, wait. I am looking at the notes on the third law, and this makes zero sense to me. This is the classic horse-cart paradox that apparently trips up every physics student.
Oh, yes. This is a classic.
If a horse pulls forward on a cart, the third law dictates the cart pulls backward on the horse with the exact same amount of force.
Right.
That is correct.
So if I am in a tug of war and we both pull with 100 newtons, we are tied. It's a draw. Nobody moves. How does the horse ever walk forward?
Resolving that paradox is the absolute key to mastering Newtonian mechanics. The confusion stems from mashing all the forces together into one big pile.
Oh, so we can't do that.
No. The golden rule here is that action and reaction pairs act on different objects. You have to draw an imaginary boundary around the specific object you are analyzing.
So we isolate the horse.
Yes. The cart's backward pull is acting on the horse. But what else is acting on the horse? The ground. The horse's hooves push backward against the dirt, and the dirt pushes forward on the horse.
Okay, I'm following. If that forward push from the ground, the traction is greater than the backward pull from the cart, the horse accelerates forward.
Oh, the forces don't cancel each other out because the forward force comes from the ground and the backward force comes from the cart.
Exactly. Movement happens when the net external force on the system overcomes the friction of the cart's wheels.
That clears up so much confusion. You can't combine forces acting on different objects. Okay, so we have the rules. Inertia, F equals ma, and action-reaction. Are these rules perfect? Because I know science is rarely settled permanently.
They are functionally perfect for our daily lives, but on a cosmic scale, they have significant boundaries. In the late 19th century, physicists like Ernst Mach critiqued Newton's definitions as somewhat circular.
But the math still basically worked, right?
Usually. But the most dramatic failure was astronomical. Astronomers observing the planet Mercury noticed its elliptical orbit was shifting slightly more over time than Newton's laws predicted.
The math was just broken. And rather than admit Newton was wrong, they assumed there was a hidden ghost planet right.
Yeah. The astronomer Urbain Le Verrier was so deeply confident in Newtonian mechanics that in 1859, he hypothesized a phantom planet must be hidden near the sun, gravitationally tugging on Mercury.
And he named it Vulcan.
He even named it Vulcan. Astronomers spent decades searching for a planet that didn't exist. It ultimately took Albert Einstein in 1915 with his theory of general relativity to fix the math.
Einstein to the rescue.
Yes. Einstein proved that Newtonian mechanics breaks down in extreme environments, like the extraordinarily strong gravitational field near the sun.
Well, listen, if you're sitting there sweating about your upcoming HESI A2 exam, take a breath. You aren't going to be tested on Einstein's theory of general relativity.
Definitely not.
But you absolutely do need to navigate the common misconceptions that trip people up in standard Newtonian physics. The biggest one being the difference between mass and weight.
Mass and weight are entirely different concepts. Mass is the measure of an object's inertia. It is measured in kilograms, and it is a constant intrinsic property of matter.
Well, weight is what? A force?
Exactly. Weight is a force. It is the gravitational force acting on that mass, measured in newtons. Weight is calculated as mass times gravitational acceleration.
So if an astronaut travels from the Earth to the Moon, their mass, the actual amount of matter making up their body and their inherent resistance to being pushed, does not change by a single atom.
Not one bit.
But because the Moon is smaller and has a weaker gravitational field, the pull on their body decreases. Their weight drops to about 1/6 of what it was on Earth. Same mass, completely different weight.
You've got it perfectly. Another enduring misconception goes all the way back to Aristotle, which is the assumption that heavy objects fall faster than light objects.
Which feels true in everyday life.
It does. Galileo reasoned this was false, but the most stunning proof happened in 1971. During the Apollo 15 mission, astronaut David Scott performed a live demonstration on the surface of the moon.
Oh, I've seen this video. It's incredible.
He held a heavy geological hammer in one hand and a light falcon feather in the other and dropped them simultaneously.
Because the Moon has no atmosphere, there was no air resistance to slow the feather down. They both hit the lunar dust at the exact same fraction of a second.
Proving visually that in a vacuum, all objects accelerate under gravity at the exact same rate. On Earth, that rate is 9.8 meters per second squared.
But help me connect this to the math. The hammer is vastly heavier. Doesn't the Earth, or the Moon in this case, pull on it with a stronger gravitational force?
It does, actually. The gravitational pull on the heavy hammer is much stronger than the pull on the feather. But remember the first law.
Oh, inertia.
Exactly. Because the hammer has more mass, it also has proportionally more inertia. It is significantly more stubborn. It requires far more force just to get it moving.
Oh, I see. So those two factors, the stronger downward pull of gravity and the stronger internal resistance to moving, they scale perfectly together and cancel each other out.
That is why they fall at the exact same rate. It is only the interference of air resistance on Earth that tricks us into thinking heavy things naturally fall faster.
Let's bring this all back down to Earth. Specifically, we need to bring this physics directly to the hospital floor. Because if you're studying this for a nursing career, Newton's laws aren't just abstract trivia.
No, they're the biomechanical foundation of your daily practice.
Let's talk about safe patient handling. It relies entirely on applied physics. For example, nursing students are rigorously trained to bend at the knees rather than bend at the waist when lifting a patient.
This is a direct application of managing torque.
Torque being rotational force.
Yes. When you bend at the waist, your spine acts as a fulcrum, and your upper body becomes a long lever arm. The force of the patient's weight multiplied by the distance of that lever arm creates a massive amount of torque on your lower back.
Which is how you blow out a disc.
Precisely. By bending at the knees and getting lower, you bring the patient's center of mass much closer to your own base of support. You shorten the lever arm, drastically reducing the torque on your lumbar spine and preventing career-ending injuries.
Wait, looking at how mechanical lifts and gait belts work in the notes, it's all about increasing the surface area of the applied force.
Right.
That is basically a giant airbag for a patient's weight.
Yes.
It's just manipulating the area and the time of the force.
That is a phenomenal way to visualize it. When a car crashes, an airbag deploys to spread the massive deceleration force over the entire surface area of your torso and face, rather than concentrating all that force on the tiny surface area of your forehead hitting the steering wheel.
Right, which would be catastrophic.
A wider gait belt or a sling on a mechanical lift does the exact same thing. It takes the upward force required to fight gravity and spreads it out over a large area of the patient's back and thighs. Lowering the pressure on any single point prevents severe bruising and skin tears on fragile patients.
And what about fall prevention? That is a massive safety metric in any care facility.
Fall prevention is deeply tied to the first law, inertia. Imagine an elderly or sedated patient who has been lying in bed. Their body is in a state of rest.
Okay, so their inertia wants them to stay at rest.
Right. If they rise to a standing position too quickly, their cardiovascular system might not adjust fast enough, causing a drop in blood pressure known as orthostatic hypotension.
Oh, I've had that. You stand up and get super dizzy.
Exactly. If they begin to lose their balance, their body, obeying inertia, simply continues moving toward the floor.
Because there is no external force strong enough to stop them until they hit the ground. Which is why the standard of care is to intervene before that happens.
Yes. You have the patient sit on the edge of the bed and dangle their legs. You give their physical state time to stabilize into a new resting inertia before introducing the complex, unbalanced forces of standing and walking.
Every time a medical professional assists a patient, they are performing a highly practical, high-stakes physics experiment.
They really are.
Okay, we have covered an incredible amount of ground today. Here are the 5 rapid-fire takeaways you need to lock in for your exams. Ready?
Go for it.
Number 1, inertia. An object at rest stays at rest, and an object in motion stays in motion until a net external force forces it to change. Number 2, F equals ma, force equals mass times acceleration. A massive object requires a massively larger push to achieve the same acceleration.
It's the bottom.
Number 3, the third law. Action and reaction forces are equal and opposite, but they act on different objects, which is why a horse can pull a cart without the forces canceling out.
So important.
Number 4, mass versus weight. Mass is your constant intrinsic inertia. Weight is the force of gravity pulling on that mass, and it changes depending on what planet you're on. And number 5, in a vacuum, all objects fall at the exact same acceleration, regardless of mass, because a stronger pull of gravity on a heavy object is perfectly offset by its higher inertia.
If we connect this to the bigger picture, there is one final concept from the fringes of our source material that fundamentally shifts how we view every single interaction we discuss today.
Oh, plot twist. I'm ready.
Throughout this deep dive, we have talked about force as a physical push or a pull between solid objects. A hand on a cart, a foot on the floor.
Right. Physical contact.
But quantum physics reveals that at the subatomic level, there is no true contact. What we experience as a solid force is actually the exchange of invisible field-carrying particles.
Wait, really?
Yeah, in the case of electromagnetism, which governs the interactions between the atoms in everyday objects, those particles are photons.
Photons, as in particles of light.
Yes. The next time you physically push a heavy hospital bed or lean your weight against a wall, remember, you aren't actually touching it in the traditional sense.
This is wild.
The electrons in the atoms of your hand are violently repelling the electrons in the atoms of the bed, and they are doing this by aggressively throwing invisible light particles, photons, at each other to create that repulsion.
That is deeply weird. So what feels like a solid physical push of muscle against metal is actually a subatomic light show.
Pretty much.
It's just an invisible field of electromagnetic energy keeping my hand from passing straight through the bed.
The rules of Newton govern the macro world perfectly, giving us the math to launch rockets and lift patients safely. But underneath it all, the mechanics are far stranger than we can perceive.
Well, my mind is thoroughly blown. Thank you for joining us on this deep dive. We started by exploring the mechanics of a car crash and the invisible architecture of everything we do, and we ended up with invisible particles of light bouncing between our hands in a hospital bed. Keep questioning why the world moves the way it does, and good luck on those entrance exams. We will catch you on the next one.